Dear students, welcome to the fourth session of our chapter 11, the P block elements. Today, in this session, we will deal with the topic allotropes of carbon. As we know, the property is the elements, those who are having the different physical properties but the same chemical property they are exhibiting, we say it is the allotropes of that element, and the property is named as allotropy. So carbon is having the different types of allotropes. That is, it will be having the crystalline as well as amorphous allotropes. The crystalline forms are the diamond and the graphite, which is the well-known forms. In 1985, the third form of carbon, which is known as fullerenes, was discovered by H.W. Croto, E. Samley, and R.F. Curl. For this discovery, they were awarded Nobel Prize in 1996. So, we know that there are three crystalline forms, that is diamond, graphite, and fullerenes. Let's see the first type, that is diamond. It has a crystalline lattice, and in diamond, each carbon atom undergoes sp3 hybridization, and it is linked to four other carbon atoms by using its hybridized orbitals in tetrahedral fashion. The carbon-carbon bond length is here 154 picometer, and the structure extends in space and produces a three-dimensional network of carbon atoms, which is very difficult to break, the covalent bond. That's why we are saying the diamond is the hardest substance on earth. Let's see the diagram of a diamond, or the structure of a diamond. You can see here the spheres. Dark spheres represents the carbon atom. And you can see one of the carbon atom, if you take, it is linked with four more carbon atoms. And each carbon atom is sp3 hybridized. So this structure is a three-dimensional network of carbon atoms. Now, let's see about the graphite. How is the structure? It has a layered structure, and these layers are held by weak van der Waals forces. And the distance between the two layers is 340 picometer. Each layer is composed of a planar hexagonal rings of carbon atoms. That is, the carbon-carbon bond length within the layer is 141.5 picometer. Within the layer, it is 141.5 picometer. And what about the difference between the two layers? That is 340 picometer. Each carbon atom in hexagonal ring undergoes sp2 hybridization and makes what 3 sigma bonds with the neighboring carbon atoms. The fourth electron is delocalized over the whole sheet or the layers. So what happens is they will be mobile throughout the layer, and they will conduct easily the electricity, and it is very soft and slippery also. Now let's see the diagram or the structure of graphite. You can see here the hexagonal sheets where the carbon atom is one of the carbon atom. If you take, it will be linked with three more carbon atoms. That means they are giving the 3 sigma bonds, and the one electron there for the valency of carbon is free or delocalized. That makes it more conducting, right? And the difference between the two layers is 340 picometer. Within the layer, the carbon-carbon bond length is 141.5 picometer. So this is about the structure of graphite. Now, if we talk about the use of diamond, as we know that it is used as an abrasive for sharpening hard tools, in making dyes, and in the manufacture of tungsten filaments for the electric light bulbs. Uses of graphite, if we talk, it is used as a dry lubricant in machines running at high temperature where the oil cannot be used as a lubricant. So these are the main uses of diamond and graphite. The third type of allotrope is the fullerenes, and it is made by heating the graphite in an electric arc in the presence of inert gas like helium or argon. And it is the only pure form of carbon because they have smooth structure without any dangling bones. Fullerenes are cage-like molecules where we can see the carbon number is 60. That means C60 molecule which has a shape like a soccer ball, which is named as Buckminster fullerene. You can see here a soccer where we can see the number of carbon atoms in a three-dimensional structure, which is a giant molecule, right? And it has what 26 membered rings and 12 5-membered rings. That means in this soccer itself, what you can see the pentagon shape where the 5-membered ring is there. Along with that, you can see the 6-membered ring also in this structure. That there's a count, that is 26-membered rings and 12 5-membered rings are present in fullerenes and makes a cage-like structure. So it is named as what Buckminster fullerene also. A 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with the 6-membered rings. So this is a specialty of the 6-membered and 5-membered rings. All the carbon atoms are equal and they undergo sp2 hybridization in this structure. And each carbon atom forms 3 sigma bonds with the other 3 carbon atoms. And the remaining electron at each carbon is delocalized or mobile. This ball shaped molecule has 60 vertices and each one is occupied by one carbon atom. And spherical fullerenes are also named as buckyballs in short. So it's a name that is given to fullerene, buckyballs. So these are the specialties of fullerenes. The other forms of the elemental carbon, like carbon black, coke, and charcoal, are all impure forms of graphite or fullerenes. The carbon black is obtained by burning the hydrocarbons in a limited supply of air, whereas the charcoal and coke are obtained by heating wood or coal, respectively, at high temperatures in the absence of air. So you can get the different forms of carbon, elemental forms of carbon. Now, when we talk about the uses of carbon, there are many uses. Graphite fibers embedded in plastic material form high strength, lightweight composites. These composites are used in the products such as tennis rackets, fishing rods, aircrafts, and canoes. Being a good conductor, graphite is used for electrodes in the batteries and industrial electrolysis purpose also. Crucibles made from graphite are inert to dilute acids and alkalis. Being highly porous, the activated charcoal is used in absorbing the poisonous gases, which the people those are going for the coal mines, which they are using the gas mask. In that gas mask, the activated charcoal is there, which will absorb. Absorb means they will the poisonous gas will be on the mask, on the surface of the mask. It will not be inhaled by the person. So there the activated charcoal is used as what the absorbing substance. And it is also used in the water filters to remove the organic contaminators and in air conditioning system to control the odor. Carbon black is used as black pigment in black ink and as a filler in the automobile tires. Coke is used as a fuel and it is used as a reducing agent in metallurgy. Diamond, as we know that it is a precious stone and it is used in the jewelries. So these are the main uses of carbon. Next we can see the silicon dioxide, that is SiO2. It is commonly known as silica and it occurs in several crystallographic forms like quartz, cristobalite, tridymite are some of the crystalline forms of silica and they are interconvertible at suitable temperatures. Silicon dioxide is a covalent three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to four oxygen atoms. You can see here the structure where we can see if you take one of the silicon, it will be bonded with four oxygen atom in a tetrahedral manner with a three-dimensional structure. Each oxygen atom in turn is covalently bonded to another silicon atom. You can see the four oxygen atoms are here. The all four oxygen atoms are linked with four silicon atoms. And each corner is shared with another tetrahedron. That means the number of tetrahedrons are here connected to each other. The entire crystal may be considered as giant molecule in which eight membered rings are formed with alternate silicon oxygen atoms. Eight membered rings are formed. How you can explain the eight membered ring? If you take this silicon and this cube you are taking, you can see here silicon 1, 2, 3, 4, 5, 6, 7 and 8. Here in this flow structure, 8 members are there with the alternate silicon oxygen bonds. Right? So this is the entire giant molecule of silicon dioxide. So you have to learn the structure of silicon dioxide, which is a covalent three-dimensional network solid. Thank you. We'll continue in the next session.